final value, that is VAB is equal to minus integral. VAB is equal to minus integral A to B E of dl. This is the basic from the basic definition of electric potential. We have obtained this equation. So later on, we have gone with the derivation part of finding of electric potential due to a point charge, and then we have seen the three cases. The first case, which is nothing but the point charge is located at the origin, and the second case, the point charge is not located at the origin, and the third case, applying of case 1 and case 2 for n number of point charges. So that is for case 3. In yesterday's class, we have seen how to derive for the case 1, that is if the point charge is not, if the point charge is at origin, and we have taken one point charge and we have placed at origin. So these are the things, and finally we have gone with the derivation, and finally we have got the final value, that is so this is the final value. VAB is equal to Q divided by 4 pi epsilon naught 1 by RB minus 1 by RA. Okay, so now we are going with the case 3. So what is that case 3? Sorry, case 2. So case 2 is so case 2, if the point charge is not at origin. So this is the case 2. Earlier case 1, we have placed the point charge at the origin, but now if the point charge is not located at origin and it is somewhere at a distance of r from the origin. Okay, so this is origin, or we are going to call this origin as a reference, and now we are going to take this our point charge. So let the point charge somewhere located at a distance of r from the origin, Now our intention is, if this point charge which is located at a distance of r from the origin, now we are moving this point charge from this location to somewhere at this location, let it be A, at this location. So therefore now what we have done some work to move the point charge which is at this location to the point A, and now we have to get the voltage at the point A. Okay, so now the distance, the new distance to the point A, now we are going to take it as RA, and now we have to find the electric potential at the location A. Okay, so at the location A. So previously the point charge Q is at this position, and this point charge Q is moved to the new location of point A, and now we need to find the difference between the potential difference between these 2 points, that is Q and A, which is nothing but VA. Okay, so comparing with previous case 1. So earlier in case 1, so this is the origin where our point charge is located, and now with respect to point A and point B, we have find the voltage potential. So earlier it is at a distance of RA, and this is at a distance of RB, and we have got the expression for VAB. Okay, so now if you want to compare these 2 cases, that is, this is for case 1, you want to compare case 1 with case 2. So earlier this is the distance vector is RA. Now in place of RA we have what? We have R. And now earlier it is RB, and now in place of RB we are having which one? This is RA. Okay, so just modifying this expression, whatever the expression that we have derived earlier. So this is the earlier expression. So in place of RB and in place of RA, we are going to substitute the new values, that is in place of RA, we are going to write the value as R. In place of RB, we are going to write it as RA. So what is our previous expression? So previous expression, that is VAB is equal to, so Q divided by 4 by epsilon naught 1 by RB minus 1 by RA. So now in place of RB, we are having RA. In place of RA, now we have to replace with R. So therefore, now the new potential, that is nothing but the potential at the location A, that is nothing but VA. So therefore, VA is equal to, what will be the value? So VA is equal to, so Q divided by, so 4 by epsilon naught 1 by RB. RB is nothing but what? RA. Now it is RA. So therefore, 1 by RA minus 1 by, in place of R, we have to write it as R. So therefore, this is the final expression for what? The final expression for electric potential for a point charge if it is not located at origin. Okay, so if Q is not at origin, if Q is not at origin, what is the value? So VA is equal to Q divided by 4 by epsilon naught 1 by RA minus 1 by R. Okay, so this is the final value for case 2. Now we are going for case 3. Case 3, that is for n number of point charges. For n number of point charges, we have to find the potential at location A. Okay, so we have to find the potential at A because of n number of point charges. Okay, so what we are going to take? We are going to take the help of case 2. We are going to take the help of case 2 to find the final expression for case 3. Okay, so for case, we are going to apply the equation of case 2 for case 3. See here, suppose this is our reference point. Okay, so here we are having the reference point, which is nothing but our origin. We are having Q1. If you are having Q1 and if you want to find the potential at A, now this is nothing but what? Our case 2. While moving, so see here, Q1 which is at a distance of R1, Q1 which is at a distance of R1, and now you are moving this Q1 to the new location of A, and this new distance is RA, and for this if you want to find the potential at A because of this point charge Q1, which is nothing but our case 2. So how we are writing that expression? That is VA is equal to, earlier we have written what? So Q divided by, earlier you have written Q divided by 4 by epsilon naught into 1 by RA minus 1 by, sorry, 1 by RA minus 1 by. Now in place of Q, you are having what? You are having Q1. So that is the small modification. So VA, so that is equal to what? So Q1 divided by, so 4 by epsilon naught 1 by, okay, so multiplied by what? 1 by RA minus 1 by R. So 1 by RA minus 1 by R, but here in place of R, you are having R1. In place of R, you are having 1 by, in place of R, you are having R1. What is case 3? So case 3 is what? So if you are having n number of point charges, so like Q1, so if you are having the Q2, Q3 and up to so on Qn, so what will be the final value? So now what you are going to take? You are going to take the second point charge, which is nothing but Q2. So let it be the second point charge Q2. So what? So I'm going to take somewhere at Q2. This is Q2. So just wait. One minute, please. Okay, thank you. Now we are going to take one more point charge. This is Q2. And because of this point charge, we need to find what the potential at A. So now this point charge Q2, it is at a distance of R2. And by moving this point charge from here to here, now you need to find the point charge, I mean the potential at A because of Q2. Now how to write this expression similarly? So VA1 means VA1 is nothing but potential at location of A because of Q1. Now you are going to find potential at A because of this point charge Q2. So there I am writing that VA2. So VA2 is nothing but potential at location A because of point charge Q2. That is equal to what? Q2 divided by, so 4 by epsilon naught 1 by RA. So because the value of RA will be the same because we are not changing the location of the location of A. So it is always at a distance of RA. So therefore this value will not change. Minus 1 by, earlier it is R1. Now what? Now the distance is R2. Now the distance is R2. Now similarly we are going to take one more point charge, let it be Q3, which is at a distance of R3. And now we need to find what? We need to find, 1 minute. Okay, so now we need to find the potential at A. So because of Q3, because of Q3. So what will be the value now? So VA3 is equal to Q3 divided by, so 4 pi epsilon naught 1 by RA minus the new distance vector is R3. So this is R3. Okay, so similarly, if you want to find the one more point charge somewhere, this is Qn. So likewise, we are having many number of point charges. Let it be Qn. So if the distance is Rn, and now we are finding the value of the potential at A because of this point charge as Qn. So what will be the value? So Van will be equal to Qn divided by 4 pi epsilon naught 1 by Ra minus 1 by Rn. 1 by Rn. So now what is the thing? What the thing we need to find is what is the final value of electric potential at location A because of Q1, Q2, Q3 as well as Qn. So that is nothing but we have to obtain the final value of VA. The final value of VA will be what? The potential at location A because of Q1 plus the potential at A because of Q2 plus the potential at A because at location of Q3 and up to so on Qn. So that is nothing but a VA1 plus VA2 plus VA3 plus and so on the final because of what? Plus VAN. Okay, so earlier we have find because of individual point charges, but now what we have to do? We have to find the cumulative sum of all the point charges at location A, so that we will get the case 3 final value. What is the case 3? We have to find the potential at location A because of all n number of point charges. Okay, so now what will be the value, final value? That is nothing but VA. So VA is equal to VA1 plus VA2 plus so VA3 plus and so on plus VAN plus and so on VAN. Okay, so what is the value of VAN, VA1? So VA1 already we have find. So this is the value of VA1. Okay. So VA1 is equal to what? So Q1 divided by, so 4 pi epsilon naught 1 by RA minus 1 by R1 plus what is VA2? VA2 is nothing but Q2 divided by 4 by epsilon naught 1 by RA minus 1 by R2. So similarly, we have got VA3 also. What is VA3? So Q3 divided by, so 4 by epsilon naught 1 by RA minus 1 by R3. So plus and so on. What about VAN? VAN is nothing but Qn divided by 4 pi epsilon naught 1 by RA minus 1 by RN. So these are all the individual expressions that we have already derived before. So see here, if you observe the above equation, so here you are having one common term, so that is 1 by 4 pi epsilon naught and also 1 by RA. So therefore divided by 4 by epsilon naught as well as 1 by RA, which is in common for all the expressions. Here you are having Q1, Q2, Q3 up to so on Qn. So it is following one sequence. So similarly here you are having 1 by R1, 1 by R2, 1 by R3 and up to so on 1 by R1. So here also it is following one sequence. So if you want to write it in the form of a sequence, that is nothing but in form of sigma, that value sigma I is equal to 1 to n. So in place of Q1, Q2, Q3 up to so on Qn, I can write it as Qi 1 by Ra minus 1 by Ri. So which is nothing but what? So this is the final expression. So therefore, what is the value? Electric potential at, so electric potential at location A. So what is the value? So VA is equal to sigma I is equal to 1 to n Qi divided by 4 pi epsilon naught. So 1 by Ra minus 1 by Ri. So this is the value. So this is the value for case 3. But if you want to write it in general, so in general, at jth location, earlier we have find at 8th location. Now if you want to find at jth location, what will be the value? So in place of A, we are going to write it as J. So what is the value? So Vj is equal to, so sigma I is equal to 1 to n. So Qi divided by 4 pi epsilon naught. So 1 by R. So in place of A, we have to write it as, in place of A, we are going to write it as J. So 1 by Rj minus 1 by Ri. So which is our final expression for the potential at jth location. Okay, so due to n number of point charges, due to n number of point charges. Okay, so this is the case 3. So this comes under what? A single question. So which is nothing but finding of electric potential for a point charge. Finding of electric potential for a point charge. Yesterday's class we have got for case 1, and today we have explained for case 2 as well as for case 3. Okay, so for case 2 and case 3. So you have to write, if they are asking for an essay type question, you have to write all the three cases, case 1, case 2 and case 3 separately. Okay. So this is what electric potential due to a point charge. And now we are going with the next topic, which is nothing but Maxwell's second equation. Maxwell's second equation. So earlier you have seen the first equation. So Maxwell's first equation. So do you remember that? Maxwell's first equation. I think you have already got this question in your first mid examination. Okay. So Maxwell's first equation, which gives what? So rho v is equal to del of d. So it gives the relation between what? So volume charge density and electric flux density. So similarly, the Maxwell's second equation also is giving one relation. So relation between two parameters. What are those two parameters? Okay, so Maxwell's second equation, it is going to give the relation between the two parameters, that is E and V. So E is nothing but electric, so field intensity, and V is nothing but electric potential. Okay, so now we are going to obtain the relation between E and V. As I told that, so all the Maxwell's equations, they are going to be related with the del operator. Okay, so del operator. So here also we are going to relate the electric field intensity and electric potential with the del operator. How we are going to relate that? We are going to derive the relation between these two parameters right now. So earlier, by the basic definition of electric potential, so we know that V is equal to what? So formula is minus integral from A to B E of dl. So this is the expression that we have derived in our previous class, that is electric potential V is equal to minus integral from A to B E of dl. Now what we are going to do? So we are going to differentiate the above expression on both sides. So if you do the differentiation on both sides, we can remove this integral. So therefore dV is equal to minus E of dl. dV is equal to E of dl. So now the next step is expressing dV. Okay, so expressing dV in differentiable equations with respect to rectangular coordinate system. So that is by using the differential equation concepts, and we are expressing the value of dV in differentiable equations and that too in rectangular coordinate system. So as I told that by default we are going to take rectangular coordinate system for simplicity. Okay, so if you want to write the value of dV in differentiable equations with respect to rectangular coordinate system, that value will be, so dou V by dou x into dx plus dou V by dou y into dy plus dou V by dou z into dz. So this is the way how we are going to write the value of dV, expanding the value of dV with respect to xyz coordinate system, that is nothing but the rectangular coordinate system, and writing with respect to differential equations, that you know how to write it, that we have already seen in your engineering maths subject. So here we are not going to explain all those things. So this is the way how to write if you want to express any differentiable variable with respect to differentiable equations and in rectangular coordinate system. So see here, Now I'm going to write this entire expression, that is dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz. I'm going to write, I'm going to express this entire expression in a new way. For that, I'm using unit vector multiplication. So if you remember that one, unit vector multiplication, dot product between similar unit vectors, dot product between two similar unit vectors. So if you remember, I'm writing again here. So that is ax bar dot ax bar and ay bar dot ay bar, as well as az bar dot az bar. So their value is equal to 1. So similarly, dot product between any different unit vectors, that value is 0. So by using this concept, I'm going to rewrite the above expression. I'm going to rewrite this entire expression as below. So how we can write means, so see here, dou v by dou x into ax bar. So please listen carefully. Dou v by dou x into ax bar plus dou v by dou y into ay bar plus dou v by dou z into az bar. If you multiply this value with dx into ax bar plus dy into ay bar plus dz into az bar. So let us check what will be the final value of these two expressions. Okay, so how we are going to do? So we are going to multiply. So we are going to take the first term. So that is dou v by dou x into ax bar, and we are going to multiply with each and every term of the second one. That is we are going to multiply with each and every term. So that means we are going to do dou v by dou x ax multiplied by what? The first term is dx ax bar. So see here, if you do the product between these two, so that is ax bar dot ax bar, the value is 1. So final value will be what? So dou v by dou x into dx. Dou v by dou x into dx. Similarly, what will be the second term? Dou v by dou x into ax. So this is the first term multiplied by the second value, that is dy by dy ay bar. So if you do the product between two different unit vectors, that is ax bar dot ay bar. So I told that if you do the product between two different unit vectors, that value is 0. So what will be the value? So its value is equal to 0. So what is the third term? The third term is dou v by dou x into ax bar multiplied by dz az bar. So the value is again 0. So therefore, see here. So if you do the multiplication of first term with the all the terms are in the second, that is the value you are getting, only the one value you are getting. What is that value? So its value is dv by dx into dv by dou x into dx. Remaining all the terms is becoming 0. So similarly, if you do, so if you take the second term, and if you do the product with the all the terms, that is dx ax bar plus dy dy bar, so you will get only the one term. That term will be dou v by dou y into dy. Dou v by dou y into dy. So similarly, if you take the third term, so if you take the third term and do the product with all these terms, you will get the value. So what is that value? That is, you will get only the one value, that is dou v by dou z into dz. So therefore, if you do the product between this term and this term, you will get what is the value dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz, which is nothing but our above expression. So this is our above expression. So what now can I write the value? So now how I am writing this above value? So whatever the value I have got, that is this value. In place of dv, now in place of dv, I am going to write this term, and in place of this terms, I am going to write as this a multiplied by this term b. Okay, so see here, I am writing. So earlier, what is the value? So dv is equal to minus e of dl. So in place of dv, how I have written? So I have expressed this dv as what? As dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz. So this is equal to minus e of dl, which I have expressed by using differentiable equations in rectangular coordinate system. And again, I am rewriting this entire term as two product terms, that is dou v by dou x into ax bar plus dou v by dou y into ay bar plus dou v by dou z into az bar multiplied by dx ax bar plus dy ay bar plus dz az bar is equal to what? So this term, that is equal to minus e of dl. So if you do the product of these two terms, again if you do the product of this entire term with this entire term, what you will get? You will get this final, you will get this expression only. So therefore I am rewriting. How we are going to get this expression means, so here I have clearly explained. So see here, we know this term. So this is nothing but what? So this is nothing but so dx ax bar plus dy ay bar plus dz az bar. So this term already we have seen in case of differentiable rectangular coordinate system. So this gives, this entire value will give as dl. So if you want, if you don't remember, please go back to your previous pages, this where you can find this expression. So that is in differentiable rectangular coordinate system, the differentiable line length will be dx ax bar plus dy ay bar plus dz az bar. So therefore the above expression, so in place of this entire term, I am writing the simple value as dl. So therefore dou v by dou x into ax bar plus dou v by dou z, sorry, dou y by dou v by dou y into ay bar plus dou v by dou z into az bar. Now replacing this entire value with the dl. So this is equal to what? Minus e dl. That is equal to minus e dl. Now on both sides you have dl and you have dl, so you can get cancelled out. So final value dou. See here, in each term you are having v, v and v. I am taking common v. I am writing the expression dou by dou x of ax bar plus dou by dou y of ay bar plus dou by dou z of az bar multiplied by v is equal to minus e, is equal to minus e. So if you remember del operator in rectangular coordinate system, we have given the formulas for del operator in all the three coordinate system. So please go back to your previous pages and verify. del operator in rectangular coordinate system is nothing but this term. So therefore, del will be equal to what? Dou by dou x of ax bar plus dou by dou y of ay bar plus dou by dou z of az bar. So therefore, I am replacing this entire term with what? Del. So therefore, del of what is the value? So del of v is equal to minus e. So therefore, rewriting the above expression, how can rewrite? So this value, this implies, so E is equal to minus del of V. E is equal to minus del of V, which is the what? Maxwell's second equation. Maxwell's second equation. So which is very much important as first equation. Okay. So here also we have got the relation between electric field intensity E and electric potential by making use of del operator. So earlier first equation, that is rho v is equal to del of v d. So here also we have related these two parameters by using del. Here also we have related these two parameters of potential and intensity by making use of del operator. Okay, so this expression is also equally important with respect to Maxwell's equations. Okay, so first equation already completed, and now we have completed second equation, and finally we are having, as I told, total we are having 4 Maxwell's equation. So among those 4 Maxwell's equations, we have covered first equation as well as second equation. Okay, so and remaining third and fourth will come in our next coming units. Okay, so this is all about what? Maxwell's equation. Maxwell's equation. Okay. So Naushad, please, Naushad, so please
recording stopped.
Take the screenshots of today's participant and send me. And ACID CR also try to take down the attendance. Okay.